So, there is an important property of these symmetry operations which you can easily see, and that is the origin of the name point group, space group and so on, that they form a group. Symmetry operations of an object form a group. So, they always occur in groups, they do not occur separately. So, what exactly is a group? So, group is a mathematical concept. So, we will define that. Let us define group. So, a set, you for a group you need a set of elements, and you need a binary operation, means a way of combining two elements. So, a set with a binary operation will called a group if it satisfies certain conditions. And what are those conditions? If, so let us say a set G with a binary operation, some binary operation. So, first property which a group should satisfy is the closure property. That is, if A belongs to group and B belongs to group. So, the combination of A and B by binary operation. So, let us say binary operation dot. So, then A dot B also belongs to the group, it should not go out of the group. So, let us consider a set 1, 2, 3, and with the binary operation plus. Is it closed? It is not closed. 2 plus 3 is equal to 5, and it does not belong to the set. So, this is not a closed set under the binary operation of addition. So, if we want to have a closed set under binary operation of addition, what will I have to do? So, that is the entire natural numbers we will have to take, then only it will become closed. No?
Identity?
No, I am only looking at the property closure at the moment. So, it is closed under plus. The second property is associative. This says that if you have 3 objects, then does not matter, and you are combining these 3 objects. So, since you have a binary operation and you have to combine 3, you do not have a ternary operation. So, since you have a binary operation, you have to combine 3 objects, you have to decide whether you have to combine A and B first and then combine it with C, or you combine B and C first and then combine it with A, and it should not matter if it is associative, it is demanding that it should not matter. So, our plus naturally satisfies this. So, we do not worry about this, because 1 plus 2 plus 3, the result does not depend upon which way do we do the addition. So, natural number n is associative with respect to plus. The third thing we require is an identity. There should be a special element called identity. Now, identity is represented by various symbols, often either by 1 or by E, because the normal way of looking at the binary operation is to call them multiplication, and in multiplication 1 acts like an identity. Sometimes we use the symbol E as an identity. So, what is identity? AE should be equal to EA, should be equal to A. So, this element, whichever way you combine with any given element, either by pre multiplication or by post multiplication, should not change your element. So, is the natural number is having the identity operation with plus? What you require for that? 0. So, what is that called? N plus 0 whole number. Let us say n plus 0, whatever that is called. So, this will have 0, 1, 2 and everything up to infinity. So, 0 is identity with respect to the binary operation plus. Because it leaves, so either I have 0 plus 1 or 1 plus 0, it will remain 1. In general, A plus 0, 0 plus A is A. So, now we have identity also, but still it has not become a group, because we have the final requirement for group is inverse. So, what is inverse? There is an element A inverse for all A belonging to G, such that if you combine A and A inverse or A inverse and A, you should get the identity. So, what is inverse with respect to addition? Negative number. So, inverse of 2 should be a number which when combined with 2 gives me the identity, and identity for addition is 0. So, 2 plus 2 minus 2 is 0, but we have not included that, we have not included the negative integers. So, I now have to add the negative numbers also. So, I will get the set of integers if I want a group. So, n is not a group, n plus 0 is also not a group, but z with all negative numbers included. Now, it forms a group. So, we will say integers, set of integers is a group under plus, n with 0 also is not a group, because inverses are missing. Other 3 properties were there, inverses missing. So, what has all this to do with symmetry? So, if you now look at symmetry, symmetry also, what will be a binary operation for symmetry? So, symmetry is an operation, symmetry itself is an operation. So, for example, when we say reflection, that is an operation, rotation, that is an operation. So, our set is set of symmetry operations, our set G is set of symmetry operations. So, for example, we saw that this H, which was highly symmetric, has a vertical mirror, horizontal mirror and a two-fold. So, it was having, so what are its symmetry operations? So, let us call this let us call this MV, let us call this MH, and let us call this a 2. So, it has a symmetry operations MH, MV, 2 and identity which we call 1. But the symmetry operations are itself elements now, they are elements of the set. So, elements of the set are operations, but for group we require a binary operation. So, we require another operation which combines these two elements or any two elements in this. What will that operation be? 2 times, one after the another. So, followed by followed by I can combine. When I say I will combine two operations, so I will say one operation followed by another operation. Combine a horizontal mirror with a vertical mirror. So, first reflect horizontally, then reflect vertically. So, with this definition now, that I collect all the symmetry operations of an object and I combine them by the operation of followed by, does it form a group? So, let us explore that. So, let us look at one by one. The first property was closure. What was the defining requirement for being a member of this group? What operations we collected in this group? No, combination. Why is MH qualified to be part of this group? Because MH left H unchanged. So, if MH leaves H unchanged and MV leaves H unchanged, so a combined operation of MH followed by MV obviously will leave it unchanged, and if that is also leaving it unchanged, so that should also be a part of the group. So, means in my list of symmetry elements or symmetry operations of H, I cannot miss combination of MH and MV, because MH is leaving H unchanged, MV is leaving H unchanged. So, how cannot MH followed by MV be not part of that set? That is also leaving it unchanged. So, that also should be a symmetry operation, but I have not written MH combined MV. So, closure is demanded that if A then AB is actually A followed by B. First we apply B, no sorry, it is B, yeah, first we apply B and then A. So, A followed by B, yeah, A followed by B, this should also belong to G, because it leaves object unchanged by very definition. So, if A is a symmetry operation, B is a symmetry operation, the combined element A B has to be a symmetry operation, you have no other way out. So, the closure property has to be there. Associativity we have to check, but usually it is always satisfied. So, in this case again what can happen? Nothing else can happen, they have to be the same. A B leaves it unchanged and then you combine it with C, that also leaves unchanged. So, the net result of the left hand side A B applied first and then C is leaving the object unchanged. The right hand side also leaves the object unchanged, because C leaves it unchanged, you combine it with B, that also leaves it unchanged, and then you combine it with A, that also leaves it unchanged. So, obviously, the two are equal by very definition of symmetry. So, associativity is also satisfied. Identity, doing nothing leaves it unchanged and we have called it 1. So, identity is also there, and if you apply some symmetry operation, if I apply horizontal mirror and then do nothing, what is the resultant? Horizontal mirror. So, the doing nothing does qualify as an identity operation. What about inverse? So, if I apply a horizontal mirror, I reflect and then I reflect again. What is the reflection of a reflection? The original object. So, reflection of a reflection is the original object, means you are doing nothing. So, that is an identity. So, M h is its own inverse, M h inverse is M h, M v inverse is M v, and 2 inverse is 2. So, inverses are there. Now, but inverses are there, identity is there, we have not yet ensured that whether the products are there, all combinations should also be there. So, now since we are having these elements, we need to ensure that M h M v, M v M h, M h 2, 2 M h, M v 2, 2 M v, these all should be part. Because they are also symmetry operation, they are also leaving the object unchanged. Where are they? M h M v तो है ही नहीं. M h M v is 2. Let us see how it is 2. Let us try to prove that. Let us say we have an object and we have a 2 mirrors. We have A, this is M v, this is M h. Let us first apply M v. So, we are doing this operation, first M v and then M h. So, first we apply M v. So, we reflect in the vertical mirror, I generate the point B. Now, actually although it is a point, we have to keep in mind that reflection changes the so called chirality, that is handedness. Reflection will change a left handed coordinate system to a right handed coordinate system. In point it is not obvious, but suppose what will happen, suppose what will happen if I have a right handed coordinate system, x cross y is pointing up, I reflect it in this red mirror. X prime cross y prime pointing down. So, if we call this a right handed coordinate system or a right handed object, this is a left handed object. So, although we will draw points, we will imagine that actually that point is representing not only a location, but some sort of a right handed object at that location. So, let us say that A is a right handed object. Then what will become of B? B will be a left handed object. Now, I apply another operation, because I have to apply M v followed by. So, I come here. Now, if a left handed object is reflected, then you get again a right handed object. So, I get C which is again a right handed object. So, the net result of m v followed by m h is A going to C directly. And by what operation A will go to C directly? 180 degree rotation. And what does rotation do to the handedness? It does not change. So, a right handed object going 180 degree opposite with the same distance, that you can prove geometrically, that this distance d is same as this distance d. So, a right handed object located here at arm's length is going 180 degree away to arm's length, then what is the operation which is relating the two? 180 degree rotation about the vertical axis. That is why we were. So, now that surprise is explained, or that observation is explained, if at all that was a surprise, that whenever we were seeing two mirrors in any of the letters here, the two-fold was always there at the sitting at the center, because the combination of the two-fold mirrors itself is a two-fold. So, this is where that group property is coming. So, actually MH and MV are included as 2, because we have included 2 in the group. So, the product of MH and MV is 2. You will find that MV MH is also 2. What will be MH2? MH2 will be MV. Remember, MH2 cannot be 2. Why?
Because for using MH you have changed the handedness.
Yeah. Using MH you are changing handedness. Using 2 you are not changing the handedness. So, the net result is a change of handedness, and a change of handedness cannot come from 2. So, MH and 2 will give you MV. So, everything is consistent. So, we get a nice group. So, that is the reason why we use the word group of symmetry group. So, symmetry operations of an object forms a group under binary operation followed by. And we have seen that one concrete example we have seen. We just finished the lecture with the what is called a group multiplication table. Table of symmetry operations of H. By the way, since this is having two mirror planes and a two-fold axis, there is a so called Hermann Mauguin symbol for it. Which is called MM2. So, one M represents one mirror, another M represents another mirror, and 2 represents the two-fold axis at the intersection point. So, let us create a group multiplication table for this. So, what we mean by group multiplication table? we just have to write all the elements. Both horizontally and vertically. So, let us start with the identity 1, then 2, then MH and then MV, and I write 1, 2, MH, MV. All you have to do is to, in any box now, I will fill the row, the column element multiplied by the row element. So, 1 into 1 is 1, thankfully. 1 into 2, identity being combined with any operation. So, we will leave it unchanged. So, that row is easy for us to write. Similarly, if I do 2 into 1, so that will remain 2. So, the column also is easy to write, the first column. Now, the other, this 3 by 3 9 elements, you have to be careful. So, 2 into 2 gives you what? 1, 2 into 2 1, 2 into MH, MV, 2 into MV, MH, MH into 2, MV, MH into MH, 1. Reflection is its own inverse. This is a strange group, interesting group, where each element is a self inverse. Do not think that this is a common property, that elements are their inverses. If you are seeing only this group, we may conclude that, but this will not be true, as we will look at other groups. So, in this case, each element is its own self inverse. MH into MV 2, MV into 2, MH, MV into MH 2. So, you can see a beautiful table has been formed, which is justifying your group property. First of all, that you did not get in this table, means we made a header of rows of all the elements and a header of columns of all the elements, and we are multiplying. On multiplication, we did not generate any new element other than the top 4 which we had written. So, that is closure. For every row, we are seeing, and we are seeing that the row of 1 is leaving everything unchanged. So, that is the identity. Similarly, column of 1 is leaving everything unchanged. So, identity is there. Then we are seeing that in every row 1 appears once. So, and that is the inverse of that particular element. So, every element has an inverse. This kind of group multiplication table, that way shows you the group structure also clearly, and ensures you that the object is a group and you are not getting anything, means it is not that the closure property is not satisfied